Okay, in this video we're going to cover a couple of main ideas. The first main idea is when I multiply a binomial that takes the form a plus b times itself, or in other words a plus b and that quantity squared, what's the product going to look like? And then we're going to do the same thing with the difference of two values, a minus b, and we're going to square that binomial, and we're going to see really that there's a pattern. And so we're going to kind of multiply those out, look for the pattern, and then we're going to use that pattern as a shortcut. So that's idea number one, and that right there is idea number two. Now, the background knowledge needed to understand this video is you need to already understand how to multiply polynomials. Now, I'm going to multiply with the box method. If you've learned some other way, that works too, but if you FOIL or distribute, you should still get the general idea. But I'm going to be multiplying with the box method, so if you understand that, you should understand this video. So before we get started, we need to understand the difference between two different things. We're going to multiply or square binomials that take this form, but how you multiply these out is different than how you multiply a single term and square it up top. Because if you've learned about your exponent properties, you would learn that xy squared is the same thing as x squared y squared. And if you wanted to verify that, you could just pick some values for x and y just to test it. Let's let x equal 3 and y equal 2. And so that means over here on the left side we'd have 3 times 2 squared. On the right side we'd have 3 squared times 2 squared. Now let's see if these end up being the same thing. We'll see if they're equal. 3 times 2 is 6. And on the right side 3 squared is 9. And 2 squared is 4. So we end up, if I square 6, 6 times 6 is 36, and that's equal to 9 times 4, which is 36. So we kind of confirm that those are equal, that you do that rule. Now let's use the same logic down here, and the reason I'm doing all this, I want you to understand, is that a lot of students are going to want to say that x plus y squared is the same thing as x squared plus y squared. They're going to want to try to take that exponent and stick it onto both the same way that we do when we square a single term. And so I want you to understand that this is not something we can do. So let me back up a little bit. And the way that I'm going to show you this is we're just going to show that it's not equal to x squared plus y squared. We're going to do it the same way we did up top. We're going to pick values for x. Let's once again say let x equal 3 and y equal 2. And we're going to see if the left side of this ends up being equal to the right side. So on the left side we have substitute in 3 in for x and 2 in for y. And on the right side of the equation, I'd substitute in 3 in for x and 2 in for y. And we're seeing if these are equal. So 3 plus 2 is 5, so that's 5 squared. Oops, I forgot to substitute in for y. And on the right side of the equation, we have 3 squared, which is 9, and 2 squared, which is 4. And so if I simplify the left side of my equation, we end up with 25 and 13. We know that those are not equal. Therefore, this is not the same thing as this. So that's kind of, we haven't really gotten to the meat of what we're talking about today, but I think this right here is an important idea, knowing that I cannot just take that exponent and stick it onto both. That does not work because they're not equal representations. They're not equivalent. So keep that in mind as we move forward. Now, here's what we're going to do. Notice how all of these binomials that we're squaring take a pattern. It's something plus something squared. Something plus something squared. Something plus something squared. This is what we're going to be working with. So I'm going to multiply these out using the box method. And the way we're going to do it is first we need to understand that any value squared is really just that value times itself. That's what it means whenever we square something. So if I work this out as if it's x plus 2 times x plus 2, I can multiply that out with a box. X plus 2 times x plus 2. X times x is x squared. 2 times x is 2x. 2 times x is 2x. And 2 times 2 is 4. I see that I have a couple of like terms right there that I can combine and simplify my answer to x squared plus 4x plus 4. Okay? Now, we've done one. Let's do another couple, and then we're going to look for that pattern that I keep referring to. So here we're going to do x plus 3 times x plus 3. In my box that we're doing for the box method, I'm going to set it up the same way. And x times x is x squared, x times 3 is 3x, 3 times x is 3x, 3 times 3 is 9. So once again, I see like terms in those diagonal boxes that are equivalent, so I can just basically double that 3x to get 6x. And then once again, we end up with a 9 there from the 3 times 3. Last time we ended up with a 4 there from the 2 times 2. So I'm just kind of wanting us to see some of these patterns here. Let's do the same way for this third one. We're going to do 2x plus 3 times 2x plus 3. And I can set up my box this way as well. And here we have 2x times 2x, which is 4x squared. 2x times 3 is 6x. 2x times 3 is 6x, and 3 times 3 is 9. So once I combine my like terms, we have 4x squared plus 12x plus 9. Now the hope, we're just doing very similar problems over and over again because we want to see a pattern. Our goal for this lesson is that you see this and you can jump directly to this. If you see this, you can jump directly to this. And if you see this, you can jump directly to this. Really, any polynomial or any binomial, when you're squaring it and it takes this form, we want to be able to jump straight to the answer. Now, let's kind of look for our pattern. This first term every time, this first term in all three of these, what you notice is we get that from this top left box in the table where you're basically just squaring that first value in your binomial. So whatever this first one is, if you square it, it's going to give you the first term over there. Notice how it worked for all three of them. If I square x, I get x squared. If I square 2x, I get 4x squared. Now, where does this second term come from? That's the next question. Well, that second term is coming from these two diagonal terms. So 2x and 2x, 3x and 3x, 6x and 6x. Where we get those is if I take the first term from one of my parentheses, and I'm talking about this first one up here, and multiply it by the last term in my other parentheses, or in other words, the first term times the last term, I would get this, and then I basically just double it because there's going to be another one of those. So x times 2 is 2x, and then you double it to get 4x. X times 3 is 3x, then you double it to get 6x. 2x times 3 is 6x, and you double it to get 12x. And then lastly, this number we arrive at kind of the same way we arrive at the first number in our trinomial. This is just the square of our last term. If I look back over here to my first problem, 2 squared is 4. I'm kind of running out of colors here. 3 squared would give us that 9. And once again, 3 squared would give us that 9. So there's our pattern. Let's kind of generalize it. We're going to write in a general form on the next slide. But it's basically this. If I have a plus b squared, that's a squared plus 2ab plus b squared. In other words, if I have, I'll just make up a random one, z plus 2y squared, that would be like considering z as my a and 2y as my b. And let's follow this formula. That means my a value would be z, so that's z squared, plus twice my first term times my last term, and then plus my last term squared. If I were to simplify this, it would be z squared plus, let's see, all of that would be 4zy plus 4y squared. Okay? And that's the hope, that when you see this, we can jump directly to the answer without multiplying it all out. So by this point, we've kind of talked about why the pattern's there. Hopefully this makes sense. Hopefully that transition makes sense. If not, maybe you can just memorize it or multiply it out every time. It's up to you. Now, let's talk about this one. Let's talk about when we subtract. And I'm going to try to be a little bit briefer here to save us some time because this video is getting long. So if we do the same thing here, multiplying these out with our box method as we did on the last slide, we're going to learn a rule for when our binomial takes this form and they're actually being subtracted. So here I'd have x squared, negative 2x, and positive 4. So if I combined my like terms, I would have x squared minus 4x plus 4. I'll go ahead and say we'd multiply this out again. Once again, I'm trying to save us time. And we get x squared minus 6x plus 9. And if we multiplied this out with our box method, we get 4x squared minus 12x plus 9. And you see really that these look very similar to the problems that we did when we were adding right here. It looks like the only difference is that these terms are negatives, which cause our middle term to become a negative. And just to kind of boil it down quickly, that is going to be the only difference. So if I see ones that take this pattern, and I'll just make up an example again. Let's go x minus 2z squared. My a value in this pattern would be x. My b value in this pattern would be 2z. So the form that my answer would take would be x squared, because x is my a value, minus 2 times my a value times my b value plus my b value squared. And so then if I do a little simplification, it becomes x squared. All of this becomes minus 4xz, and then that right there becomes plus 4z squared. So can we see this, recognize the pattern, and jump directly to our answer? That's our hope. Now, I want you to see why these patterns are there, why these perfect square trinomial patterns exist. That's why we multiplied all these binomials previously. But if you can't remember this pattern, or if you're scared you're going to mess it up, there is no harm in multiplying this out every time. I just want you to see the pattern in case you want to use it and save yourself some time. And so to summarize, in one step, we should be able to go from there to skip all the multiplying it out and end there. If I see the subtraction, I should be able to see that, skip all the multiplying it out, and end there. And if you can do that, you're going to be good to go.